second speaker is Professor Alastair from New Zealand. Scott, sorry. That's not intended. Yeah. I seem to be sleeping still. Okay. New Zealand is probably about as far as you can travel from land, still staying on land from Finland. So he's I guess from far away. I noticed from his vita that he's traveled around the globe at least once. Namely, he got his undergraduate degree in New Zealand, then PhD in Chicago, then he had a position in London, School of Economics, and now he's back in Auckland. So, at least once. How many other times? I don't know. A few other times. Well, his field is sample survey theory, and his title today is Generalized Linear Models with Survey Data.
Sorry to say it's not going to be nearly as exciting as Alastair McLean would be.
Best jokes are
as Professor Arjas said, what my main interest is these days is sample survey theory, and I wanted to talk about problems of fitting GLIM-like models to sample survey data. There's an example taken from the Canada Health Survey of a set of, well, this one's the health survey looking at the proportion of women who regularly screen themselves for breast cancer, classified by a large number of variables. I've just picked out age and education there. Obvious sort of thing you might want to do is fit a logistic model, perhaps look at something like the logarithm of the log odds of screening sometimes to screening never, as perhaps a linear function of age and education, or some more complicated model. The sort of thing you'd like to do, fitting a logistic model to independent observations, but of course in a big sample survey things are never simple. Structure's much more complicated. This survey is a particularly complicated one, with split up into separate samples from all the Canadian provinces, different samples from urban, rural regions, urban regions, sampling done in several, 4 or 5 stages, and then a complicated adjustment procedure at the end of all that to get the estimates. So the final structure of the data there is enormously complicated, and that's typical of all sample survey data. What we want to do with that, as I say, is the sort of things we want to do when we're using GLIM to fit data from a nicely designed experiment. Well, in general, let's suppose then I've got a table of estimated totals or proportions like that one. I'll call those P hat. And let's suppose that they're consistent estimates of the corresponding population proportions. And I want to fit a generalized linear model, or a type of generalized linear model, something like this, for the vector of population proportions. In that example, I was looking at logistic functions of the log odds of screening to not screening, or a probit model we might have. In a demographic study of migration, we might be looking at marginal homogeneity, where we want a linear function. In general, we've got some vector of smooth functions that have nice standard GLIM-like form. As I said, the problem is that the estimates we have there from big surveys have this enormously complicated, messy structure. Well, having said that, I'm going to start off with a case where they don't. In fact, with a bit of luck, in half an hour, I'm going to finish with a case. I'm going to finish with a case where they don't and never have to get into real life. Let's start with a case of stratified random sampling, where the strata just consist of a partition of the cells of the table itself. Got a simple random sample within each of these strata. So each of the strata has a multinomial distribution, so the whole vector has a product multinomial distribution. Simple, but people, at least I was going to say people, you get samples like that, or people pretend that you get samples like that. There's one taken from an article in the last Biometrics of last year, looking at trying to build a logistic model for a disease based on an environmental variable and an index of susceptibility. It's a paper by Fears and Brown in Biometrics of December '86. There, it's a sample, the population's split up into 12 strata, and then each of those strata is again subdivided into those people with the disease, those people without. So we've really got 24 separate strata, and then we take purportedly a simple random sample from each of those 24 strata. So we've ended up with a product multinomial with 24 block diagonals down the covariance matrix. They wanted to fit a simple logistic model where L of I of k again is the log odds of getting the disease to not getting the disease for given values of the environmental and susceptibility index. You might want to fit a probit model, whatever. So that's an example of the sort of thing I'm talking about. As I said, in that case, you do have a nice simple structure. You can write the covariance matrix in a, let me put that one aside so I can pull it out to look at again in a minute. We've got a nice simple covariance matrix. That's just a fancy way of writing a block diagonal of these multinomial covariance matrix. We can express the covariance matrix as a function of the mean vector P, as in ordinary generalized linear model theory. There's still a difficulty even with such a simple case as stratified random sampling, the difficulty being the singularity of this V matrix. Simple case, had a multinomial sample, the estimated proportions are all going to add up to 1, so you've got a single singularity. In a more complicated model like this, you know the number of cases and the number of controls in each of those strata, so you've got 24 different conditions. The sum of those two numbers is known to be equal to 702 and so on. So in general, we've got conditions like this where K is just the sort of one-way analysis of variance design metric. That's just saying that the proportions sum to a known constant within each of the strata. Now, that's, as I say, simple, but just to prove that it's still worth doing, there's 2 papers in recent biometrics. In fact, the only 2 papers I know that have dealt with that sort of problem and anything like that generality. That one's doing it through weighted least squares, that's one through maximum likelihood, and in fact they both get the wrong answer. Both get the wrong answer for somewhat different but related reasons. So it's simple compared with the general problem of a real life messy survey, but it's still reasonably difficult in its own right. Well, the theory, the fact that it's stratified random sampling with product multinomial covariance matrices makes no difference. You could think of a general covariance matrix, of a general singular covariance matrix essentially that means with a fixed null space, where the null space doesn't depend on the value of the parameter vector, where this V of P is some known function of the mean vector. And an example more complicated than the ones I've given would be a Dirichlet multinomial model for simple stratified two-stage sampling, where within each of those strata you drew your sample in 2 stages, a set of clusters, and then you subsample within each of the clusters. And you had a nice simple model where the proportions themselves varied across the clusters according to a Dirichlet distribution, you get a Dirichlet multinomial model, which essentially just looks like a multiple of that product multinomial model. So we could accommodate simple sorts of clustering, at least within that model. Now formally, this is just a special case of something that's been treated by Peter McCullough in a paper in the Annals in 1983, and probably by other people too. Let me write the mean vector P. I'll change my parameter to alpha to distinguish it from the beta that I had in my own model. We've got a mean vector that's a function of some alpha. We've got a covariance matrix V, which is possibly singular, but a function also of alpha, or a function of P, and hence of alpha. And he writes the likelihood, or more generally the quasi-likelihood equations in this form, just sort of the standard Glim-like generalization of the normal model, where we've got the vector of residuals, inverse of the covariance matrix, or in this case the generalized inverse since it's singular, and something that plays the role of the design matrix. It's just the matrix of derivatives of the mean vectors with respect to the parameters. And V of alpha can be any generalized inverse of P of alpha. So on the faces of anybody familiar with Glim, that just looks like a Glim formulation. The only new thing is that we can stick in any generalized inverse in place of the true inverse that we normally have. But of course, most people in this audience are familiar with the problems of singular linear models will know that that's not as easy as it looks. Let me just look at what would happen if we just proceeded naively with that. Let's suppose that we've got a sort of nice one-to-one transformation. So we have as many functions as we had starting out, as we had components to start out with. And let's suppose that that vector of functions are nice and smooth and invertible and so on, so that we can write this vector as the inverse of x of beta. In that case, the derivative of p with respect to beta is just the inverse derivative. I've called the dg dp h, so dg inverse is just h inverse with all the nice regularity conditions, I'm assuming, multiplied by the derivative of this thing in here, so it's just h inverse x. We substitute that in McCullough's expression p, just back in here, and we get something that does indeed, for anybody familiar with Glim, look exactly like the sort of familiar quasi-likelihood equations. The X matrix there, a generalized inverse of this thing, which I've called V of G because it's the asymptotic covariance matrix of G of P hat, which is fading already. Times H. The exact form doesn't matter. And again, to an audience of generalized inverse experts, they'll realize presumably immediately that doesn't work, because this expression here, the solution of that expression, depends in general on which generalized inverse you pick there. And what's more, if you pick the wrong one, the answer you get here doesn't even normalize. The probabilities you get if you pick a solution to the wrong generalized inverse don't add up to 1 or don't satisfy the constraints K transpose P equals some known function. So that naive approach doesn't work. Perhaps I should say, the attraction of that naive approach for the product multinomial type thing is that the sort of dp inverse, where dp is just the diagonal of the p inverse, that's a generalized inverse that works for all that class of product multinomial distributions. So if we could just plug that in there, in essence, that's like pretending we had a set of independent Poisson observations, so we could just get the answer to any one of our problems by running it through a standard Glim program, pretending all the observations were independent Poisson. And people in general know that can't be true. The problem lies in with this bit here. What happens is that I'm just saying that all over again. It depends on the choice of generalized inverse, doesn't normalize. The problem is that there's an implicit, that's actually, the 1983 is in the free form days of the Annals where regularity conditions weren't spelled out, and this case is one of the cases where it can lead to a problem. it's essentially the problem that were in both of those papers that I referred to, though they didn't get it from a colours paper. The condition, of course, the standard condition that this parameter has to lie in some open subset of the parameter space. We've got a constraint here. We've got L strata, say, so we've got L nonlinear constraints on our parameters. So this parameter vector there is constrained to some lower dimensional curve in our whole parameter space, and then none of the asymptotic theory goes through. It's easy enough to fix up. Well, it's just a little technical assumption to make sure we can solve those equations in general. We've got L constraints, so we split the parameter up into 2 bits. L parameters that are essentially determined by the constraints given the rest of it, and the rest of it. So let me split my model up into a bit that's free to, where the parameter is free to float around in at least a reasonable neighbourhood of the true value, and a bit that's been constrained by the constraints. So for a given value of this free bit, the rest of it can be, with those assumptions up there, can be determined directly by the constraints. So implicitly our mean vector is a function not of a k-dimensional parameter, but of this k minus L dimensional parameter beta 1. If you write it like that, then go through the same manipulations, you get something that does work all right. And just doing that is, again, a simple sort of extension of the standard work by C.R. Rao and Mitra, and I guess Ziskin and Martin on singular linear models, which are just a little bit nastier. The result is that you get a sort of normal like set of equations, just like the ones I had before, but instead of having the full X matrix there, you've essentially got the orthogonalized one. You've got in the case where you just have a single constraint, the constraint that all the probabilities add up to 1, this just means you subtract out the column mean from every one of the columns of X. So this is just the centralized value of X1. So you just have to pre-centralize, then go through all the manipulations, solve this. Though, of course, I've concealed this bit here depends on beta 1, 2, so you can't centralize once and for all. You have to keep redoing it at every stage of the iteration. Now, one of the simple case of you don't want to see, I don't think at 20 past 2. Well, perhaps I should say the asymptotic theory of McCullough doesn't work here because he's assuming the dimension of the vector of the observation vector gets bigger and bigger, whereas in most cases the dimension of that table stays fixed. But if we have some sort of central limit theorem for our survey design, which is reasonable, certainly we do have for product and multinomial design, for instance, then you can get the same sort of asymptotic normality, sort of just like generalized least squares. I'm assuming my X matrices have full rank and so on for simplicity, but that doesn't matter. And then you can solve that equation in the standard Glim-like way by iterated least squares, putting in any old generalized inverse there where you would have an inverse in the full rank case. The condition, having centralized this thing here, it's now invariant under different choices of the generalized inverse, and then we choose our beta naught, so that the conditions are always standardized and so on, so we avoid all the problems. As I say, one special case of that is very well known. You have a linear model, sort of things you have when you're dealing with marginal homogeneity or models like that. Then the matrix of derivative transformation is just the identity matrix. The centralized thing can be just centralized once and for all. It doesn't depend on the parameter. So you just pre-centralize both your X matrix and your P vector, and then go through the standard Glim type iterations. And in particular for stratified random sampling, you could just pretend everything's independent Poisson. So for linear models, stratified random sampling, provided you pre-standardize, you can just pretend the thing's independent Poisson, put it through a standard GRIM program, and it works. And that sort of general McCullough type algorithm is a generalized version of that, except that the standardization step here has to be inserted at each stage of the loop because the centralization does depend on the value of the parameter, so you have to keep redoing it. Now that's straightforward enough, but in general, one problem is that this P of t here, P of t at each stage of the iteration is the current estimate of the vector. It's P of shorthand for P of beta t, beta 1t, which, so it's equal to G inverse x0 beta 0 plus x1 beta 1. So it depends, in fact, on finding the appropriate value of beta 0 at each step of the iteration, and that depends on solving L nonlinear iterations at each step. So it's, in the linear case, it's nice. In the nonlinear case, it's still a fair amount of work to do. So it would be nice if we could go back to the simple naive case, just put our X matrix in there once and for all, and put a generalized inverse in there. And again, for anybody who was at the first Tampere symposium and went to Professor C.R. Rao's lectures and familiar with the corresponding theory for singular linear models, it's not surprising that you can find, if you take the right sort of generalized inverse there, you can do it, and that's a class of generalized inverse. I should say this is some arbitrary non-singular matrix in there. So this is the part of the design that's fixed by the constraints, if you like. You just add that on before you, and then take, that's then non-singular with the assumptions I put on, take the inverse of that, use that at each stage there. Well, it's just a little lemma to say it is indeed a generalized inverse. And you can just, those then are the likelihood equations in the case of product multinomial, more generally the quasi-likelihood equations with the appropriate probabilities. If you use that special form, which is the sort of form that Rao and Mitra used in linear models, I guess other people too, then, well, the resulting limit does satisfy the constraints automatically. The component of beta 1 is exactly equivalent to the solution of the McCullough type centralized equations, and you don't have to do any of the centralization. And it's asymptotically normal, so on. And in fact, you can get the asymptotic covariance matrix from the naive sort of thing, the sort of thing you get from generalized least squares, except that you just have to subtract this component, this matrix U, from the bits that have to do with beta 0, which are essentially the bits you're not really so interested in anyway. So if you're only interested in beta 1, you just have to take the appropriate components of that. So you can read it off automatically. You can do the proofs again. You can do the standard GLIM-like iterations without now having to, at this PT here, now is just G of inverse of beta t, doesn't require any nonlinear equation solutions. It just requires a little insert in a standard GLIM program to change the inverse you'd normally have here to this particular form of the generalized inverse. And almost everybody's familiar with the special case of that, though that would be a very cumbersome way of doing it. In the case of log linear models, where x naught's equivalent to, that's just a fancy way again of saying, in the case of log linear models where you actually put in a constant for every one of the strata is all that means, which is the case that anybody who's used to fitting with log linear models does without thinking about it. Then you know you can just, it doesn't matter whether you've got stratified random sampling or an overall simple random sample or independent Poissons, you get the same answer. Well, that's, you can see if you put U into that matrix, then this generalized inverse just falls in, just becomes the diagonal matrix of the proportions, which is just the Poisson covariance. So that's the special case of log linear models just comes to the conventional thing that you don't have to do anything fancy at all to cope with stratification. You just have to throw it in pretending it's Poisson. Non-log linear models, you have to put in, well, M isn't as simple as that, but it's not much more difficult. Well, I've got 3 minutes. That's the easy case, as I say. Real surveys are never quite like that. Even that one that I threw up as an example, which is now got buried in here. Here it is. That one, which purported to be a set of 24 independent strata. Well, in this case, if you work out from those sampling fractions, this says you'd be taking a random sample of 700 observations from a population of 180,000. And I've been in sampling for 25 years or so now, and I've never seen anybody take a simple random sample from a population of 180,000 people. Just couldn't afford to do it. So even that one, I'm sure, has some much more complicated clustered multi-stage scheme, in fact, built into those things. And that's going to mess up your covariance matrix. Well, in 2 minutes, how do you cope with more complicated things? What you do is take a good stab at the covariance matrix. So you do as well as you can with a V0. Put that in your standard program. All the second order properties, variances, and the test statistics and so on that are going to depend on them are going to be wrong now. But the estimate you get out of it is consistent, and it's asymptotically equivalent to this sort of linearized form. What you need to get the correct covariance is simply an estimate of the covariance of this, which depends on the covariance of that function there, this thing down here. That's a covariance matrix of a set of linear combinations of totals. And one thing that conventional sample survey theory is very good at is estimating variances of linear combinations of totals. So all you need to get something like that is a program that will produce variance estimates of totals, which is something that any respectable design has going for it. You can then get the correct covariance matrices out. The efficiency, of course, will depend on how well your stab is, but it's like the efficiency of ordinary least squares in general. If you're anywhere close, it's pretty good. And most of these big surveys, efficiency is not your major worry. You've got lots of observations. It's just the messiness of the structure that's your major worry. Perhaps I should just say in that last one, that's a problem, by the way, is by no means unique to sample survey theory. I think if you're dealing with clustered observations in biology, if you're an ophthalmologist dealing with pairs of eyes, or you're dealing with twin data or litter data, any sort of data where you've got clustering present, you get the same sort of thing. And if, there's a paper in a recent issue of Biometrica by Liang and Zeger, for instance, dealing with repeated measures designs, where your clusters correspond to repeated measures on the same thing. Same sort of problem. If you look at their solution, it's essentially the same solution that sample survey people have been proposing for some time. In fact, their solution is a special case of a paper by David Binder in the ISR review a couple of years ago. If you regard a repeated measures design as a simple single-stage cluster design and apply Binder's results for general survey design to that one, you get the Liang and Zeger.